Hello. So today's topic is going to be on the maximum likelihood estimation of the Gaussian function. We're going to be looking at what it actually means to be taking this maximum likelihood for the distribution that we talked about in the previous lecture. So if you're already somewhat familiar with the Gaussian distribution, you've probably heard of things such as having the sample mean, the sample variance, an unbiased estimate for the variance, or a biased estimate for the variance. So we're actually going to be looking at where all those things come from principle, in a manner of saying. So having said that, I'm actually going to get started right now. That's maximum likelihood estimation for the Gaussian distribution. So this is the topic for today, essentially. So sometimes you'll see me abbreviate this as MLE, like maximum likelihood estimation. So just so that you don't get confused when I do that. So let's actually get started with this. So imagine that we are given a data set that I will denote by X, right? So we have a data set X. I'm denoting it by a special kind of X here, which is bold in the manner of speaking. And this X comprises of X1, X2, all the way up to Xn, right? This is our data set, right? So this is our data set of observations. So while this is actually a vector, this is more of a scalar, like x1, x2, they're all scalar variables. You can think of them in that way. So we're told that observations are drawn from a Gaussian distribution. They're drawn independently from a Gaussian distributions. So observations drawn independently from a Gaussian distribution. And the idea is that this Gaussian distribution, if you remember from our previous lecture, it will obviously be parameterized by two things, which is mu for the mean and sigma squared, right? So we call this points that are drawn like independently from a distribution. There's a special term that we use for such points, and it's called independent and identically distributed. So in short, we just say IID. So independent and identically distributed. This is the name for these points that are drawn independently from the same distribution, so to say. So when we're actually looking at this and someone asks us, given these observations, we want to actually estimate what the value of mu and what the value of sigma squared is, right, from this distribution, from this Gaussian distribution that we're drawing from, right? So essentially what we're doing is we're trying to find what the values for these two things are, given that we're just drawing randomly from this distribution, and we have a term here. So what we're actually trying to estimate is the probability of the data set that we generated, right? The probability of this X given mu comma sigma squared, right? So we want to know what the probability of generating this data set given mu comma sigma squared might be, but we don't know what mu and sigma squared are. Essentially, we're actually going to be having a whole chain of events where we compute this, and I'm going to discuss how we do that. So the idea is that if you remember from before, the joint probability of two independent events is given by the product of their marginal probability, right? So the product of the marginal probability is what gives us when we have two independent events, if we compute the product of their marginal probabilities, we get their joint probability. That's what I'm trying to say here. So when we look at this, actually, since these observations are drawn independently, right? So as you know that when you have two events that are independent from each other, and you want to compute the probability of having both events happen. For instance, if you have event X, let me use a different color since this is more of a side note. So if I have an event X and I have another event Y, right? So event X, I have an event Y, then I can say, if I want to know what the probability that X and Y will happen, and if these two events are independent from each other, I can just multiply the two, say it's probability times X, probability of X times the probability of Y. This is how you essentially compute the probability of two events happening when they're independent from each other, right? This is something that we learned from the probability lectures before, so it should be clear. So here, when we're talking about this probability of this entire X vector we have here, we essentially can get it by taking the product. So this symbol is representing product of from n is equals to 1 up to n, right, of the probability of each and every one of these events happening, right? We're multiplying this. And essentially, how do we actually get this probability? Well, we have to look at the normal distribution, right? The PDF here. So we have mu comma sigma squared, right? This is how we estimate the probability of having all of these observations given mu and sigma squared, right? Since we're saying they're actually drawn independently from a Gaussian distribution, we don't know what mu is, we don't know what sigma squared is, but we just compute the probability of each and every one of those things happening and multiply it by each other. How do we get the probability? Well, we use the probability density function here that's represented. So what we're trying to do now, okay, so we are given this is how we compute the probability, but we want to figure out what these values are. So when you see this mu and this sigma squared, this is what we want to determine, right? So this is what we want to determine. What is mu, what is sigma squared? But how do we do that? Right? How do we actually compute this mu? How do we compute this sigma squared? Well, we do that by maximizing the likelihood. So we do that by maximizing the likelihood of this event. So if you remember from our previous lecture, you should know what likelihood actually is referring to in this case when we had the probability of data given some parameters which back then were representing by W, and we had called that the likelihood. So in case you don't remember what this term actually means, please just look at the previous lecture and you will know. So having said that, so we want to maximize this likelihood. Okay. But the thing is, there are a couple of problems when we actually work with this function as is. One of those problems is that it's actually difficult for us to optimize it in this form, because once you have very small probabilities, because when you're multiplying small numbers multiple times, like you might end up having some form of underflow at some point, and it becomes really difficult to actually compute those accurately. And another thing is that from a mathematical standpoint, it's actually more convenient to maximize the log likelihood than just maximizing the likelihood directly. So what are we talking about? We should maximize the log likelihood of the function above, right? And we can say that maximizing the log likelihood, right? So if we're finding the max of the log likelihood, this is essentially the same as finding the max of the likelihood. So let me just do this so that we know what we're talking about. So maximizing the log likelihood is the same as just maximizing the likelihood of the function. Why are these two things the same? Because when you look at the log function, it's a monotonically increasing function. So that means that when we maximize the log of a function, it's essentially the same as maximizing the function itself, right? So that's the point we're trying to make here. So let's actually now go deeper into how we go about doing that, essentially. So I'm going to open a new page for this because this might be a bit involved. So let's look again at the equation at hand here. So what do we know, essentially? We know that this, right, xn given mu comma sigma squared, what is this actually equal to? We know that this is 1 over 2 pi sigma squared to the power of a half times the exponent of minus 1 over 2 sigma squared times x minus mu squared, right? This is the formula for the Gaussian that we've been going through in the past two videos, actually. So we say that these events are actually, when we look at the probability of x, which I'm trying to make bold here, but yeah, given mu comma sigma squared, and this is, remember, this is IID, which means independent and identically distributed. We can compute that by taking the product from n is equals to 1 up to n of 1 over 2 pi sigma squared to the power of 1 over 2, again, times exponent of the exponent of minus 1 over 2 sigma squared x minus mu squared, right? But now we say that we want to maximize this function, but it's more convenient for us to maximize the log of this function. So first we need to actually take the log of this function, right? So to do that, we apply ln of p x given mu comma sigma squared, and this should be equal to the ln, the log of this whole expression, right? So let me just write it again just so that it's easy to follow. So I'm just repeating the same things. This is to the power of a half times the exponent of minus 1 over 2 sigma squared x minus mu squared, right? But what do we actually know about the logarithm, right? So this is just a little bit of a side note, but I'll just enter it maybe in this little corner here. We know ln a times b is equals to ln a plus ln b, right? So the logarithm of two products is equals to the log of each element of those products, right? So ln a times b is equals to ln a plus ln b. So we'll be making use of this. So instead of writing this as ln of a product, we can write it as the summation of the ln's based on this rule. So we can write this as the summation from n is equals to 1 up to n of ln, and then here we have 1 over 2 pi sigma squared, right, to the power of a half times the exponent of the same expression we had over there, minus 1 over 2 sigma squared x minus mu squared, right? So we're taking the log of this. Okay, let's keep going. Well, now that we've reached this point, we can also separate this, because this is ln a times b, so we can write this as ln a plus ln b, right? So we keep our same summation operation here, and we have ln 1 over 2 pi sigma squared to the power of a half, right, plus ln of the exponent of minus 1 over 2 sigma squared x minus mu squared, right? This is where we are. Okay, what's the next step? Well, the next step is now simplifying this. So ln, let me have another thing here, ln a over b, this is equals to ln a minus ln b. So these are just logarithm rules, in case probably you'll be familiar with this, but just in case. So what do we have here? This is summation from n is equals to 1 up to n. So this is ln 1 minus ln whatever this is on the bottom. So we've got ln 1 minus ln of 2 pi sigma squared to the power of a half, right? And then when you say ln of an exponent of a value, is just that value. So again, this is another rule, right? When you have ln e of a, this is equals to a ln e, which is equals to 1. A, sorry, what am I saying? So it's equal to a. So that's another rule we're making use of here. So ln of the exponent of this should actually just give us minus 1 over 2 sigma squared x minus mu squared, because this and this cancel out, essentially. That's the idea here. Okay, so let's keep going. So ln 1 is 0, so let's cancel this out. So what are we left with in this case? We are left with, this is equal to the summation from n is equals to 1 up to n. So let's actually separate these terms even further, right? So we can have half come here for the same reason. When you have ln e to the a comes down there. So we can have minus 1 over 2 ln, right, 2 pi. I'm now just separating the product of this ln's. 2 pi plus ln sigma squared, right, minus 1 over 2 sigma squared x minus mu squared, right? So this is what we've figured out at this point. So we have made this computation. So what's next now for us? Okay, we have reached this point. So we take the summation from n is equals to 1 up to n, right? Still the same thing we have. Then we have minus ln 2 pi over 2 minus ln sigma squared over 2, right? This is what we have. And of course, all of this is still within the summation operation. So, where is the rest? So this is minus, like we took 2 pi over 2 sigma squared over 2, right? And we still have an extra term over here. So this is minus 1 over 2 sigma squared x minus mu squared, right, from this term over here, the last term. And this is equals to summation from n is equals to 1 up to n. I'm just reorganizing it here. Minus 1 over 2 sigma squared x minus mu minus ln 2 pi over 2 minus ln sigma squared over 2. Okay, so this is the point we've reached. And what can we do? So this is obviously multiplied by everything here. So we can essentially, one thing we can do is take this summation out of this term. Let's actually take the summation of each and every one of these terms individually. So let's start with this term. So this we can write it as minus 1 over 2 sigma squared, right? Summation from n minus 1 up to n of x minus mu. I don't know why I forgot the squared term here. So yeah, right. And the next term is this one. So it's minus ln 2 pi over 2, but we're summing it n times. So this is minus n over 2 ln 2 pi. Same for this term, minus n over 2 ln sigma squared, right? So this is the result that we want. So this should be giving us what we were trying to find in the beginning, if you remember, which is the log of this probability distribution of x parameterized by mu comma sigma squared. That's what this is supposed to give us, in a sense. Okay, so now that we figured this out, let's move on to a new page. Next thing, okay, so let me just write it down here just so that we remember what it was. So ln p x parameterized by or given by mu as sigma squared is equals to minus 1 over 2 sigma squared summation from n is equals to 1 up to n of xn minus mu squared, which is another thing I had forgotten here because I had, so here everywhere where you see x, I should not have left that out. This should be xn, right, every point here, because it's all part of the summation essentially, because we have xn everywhere. So this should be xn. So just correct that. So this, we have this minus n over 2 ln sigma squared minus n over 2 ln of 2 pi, right? Okay, so first things first, we want to estimate the value of mu, and to do that we need to actually take the log, we need to maximize the likelihood with respect to mu for to be able to do that. So to be able to find the maximum likelihood in this case, what we're actually doing, how do you find the maximum of a function? With respect to some variable, you differentiate and you make that differentiation equal to 0, in a manner of speaking. So we take the derivative with respect to mu of ln p x given mu comma sigma squared, right? This is what we do. So after actually taking this derivative, let's actually look at the terms here that actually depend on this mu. So this is equal to the derivative with respect to mu, right, of minus 1 over 2 sigma squared summation from n is equals to 1 up to n of xn minus mu. So we're taking the derivative with respect to this whole term, minus 0, minus 0. The derivative with respect to mu here is 0 because there is no mu. This term does not depend on mu, and the same goes for this term. So what does this give us? So let's take the derivative here with respect to mu. So again, I forgot the square term there. So to be able to do that, first we should just take the derivative here. So by using the chain rule, you take the derivative outside, multiply by the derivative of what's inside, and so forth and so forth. So if we move this 2 here, right, we would have minus 2 over 2 sigma squared, right, summation n is equals to 1 up to n times xn minus mu. The derivative of what's inside is 1, so we just ignore this, and we make this equal to 0, right, because we're trying to find the maximum likelihood here. So these two terms cancel, right, essentially. So we're left with sorry, I might have forgotten a term here. So actually no, it should be fine as it is if we look at it this way. So if we cancel out these two terms, so it's minus 1 over sigma squared, so we reach this point. And what's the next point we're going to reach? That means that the summation from n is equals to 1 up to n of xn minus mu is equals to 0, right? So what happened to this term? We multiply both sides by sigma squared, right? If we multiply this by sigma squared, it cancels, multiply by sigma squared that side, it's just 0, so should be fine. So the next thing, there should be a minus here, sorry. So that means that the minus summation from n is equals to 1 up to n of xn, now we're separating this term, plus, now the summation from n is equals to 1 up to n of mu is just n times mu, right? Because we're just summing the same terms n times, and we equate this to 0. That means n times mu is equals to the summation from n is equals to 1 up to n of xn, and that means mu, as per the maximum likelihood estimate, should be equal to, what should this be equal to? The summation from n is equals to 1 up to n of xn times 1 over n, right? Okay, so this is our first result. And we call this our sample mean. So this is our sample mean. So now that we see that if we want an interpretation, the sample mean, we take each and every one of the components and we add them up from the distribution. Like this is the x values that we're drawing independently from the Gaussian distribution. So we kind of add them up and then divide by n. And to do that, and then we actually get the sample mean, which is just the maximum likelihood estimate of this term. Okay, so next we take the derivative with respect to sigma squared, because first of all, if you remember, let me go back, we want to estimate mu and sigma squared. First, to estimate mu, what we had to do was to take the derivative with respect to mu and maximize it by equaling that derivative to 0. Now that we're taking the derivative with respect to sigma squared, we're just trying to find the value of sigma squared, right? So we take the derivative with respect to sigma squared of ln p x given mu comma sigma squared, right? So what is this equal to? So which terms here, we're using this equation up here, right? This is the equation we're using, the one that we have here. So which terms here actually depend on sigma squared? This one, the first two terms essentially. So let's just look at those terms. So we are taking the derivative with respect to sigma squared of minus 1 over 2 sigma squared, the summation from n is equals to 1 up to n of xn minus mu squared minus, so this should be a minus here, minus the derivative with respect to sigma squared of n over 2 ln sigma squared, right? So I'm just, for the sake of making things a bit clearer, I'm just gonna say q is equals to sigma squared here, right? Let me just highlight this in yellow. Okay, just say q is equals to sigma squared. So we can take the derivative with respect to q minus 1 over 2q of the summation n is equals to 1 up to n times xn minus mu squared here, minus the derivative with respect to, again, q of n over 2 ln sigma squared. I might be breaking some rules here, but it all evaluates the same thing, so should be fine. So having done that, let's first go on by taking this derivative. What would be the result of taking this derivative, essentially, is what I'm trying to say. So if we take this with respect to q, so we have 2q minus 1, so it becomes plus, right, 2 over q squared, right, for this term, because this becomes minus 1 times 2 over here, right? So let me just show it over there. So we have minus 2q, the minus 1, this becomes plus 2 over q squared, right? That's essentially where this is coming from. So summation from n is equals to 1 up to n of xn minus mu squared minus the derivative of, no, this should not be sigma squared, this should be q, since we replaced this, so forget about this term here. Okay, So if I have an eraser, okay, that's better. So the derivative of ln q is just 1 over q, right? So this should give us minus n over 2q, and this is equal to 0, right? So what does this mean? This means 2 over q squared summation from n is equals to 1 up to n of xn minus mu squared is equals to n over 2q, right? So we multiply both sides by q squared. We have nq over 2 here, and then these 2's cancel, and then we have nq being equal to this, but we said q is sigma squared, so that means we have n times sigma squared being equal to the summation from n is equals to 1 up to n of xn minus mu squared, right? And then sigma squared is equals to 1 over n times the summation from n is equals to 1 up to n xn minus mu, right, ml squared. So this is the mu from the maximum likelihood estimate, essentially, right? This is what we got. And we can interpret this as the sample variance, right? So this is how we compute the sample mean and the sample variance. So by doing this, we have actually established, like, even if you are familiar with the normal distribution before, now you can get a basic understanding of where the sample mean and the sample variance come from, in the context that we're just maximizing the likelihood of this probability that we see over here, this probability distribution. So having said that, I wanted to get into the topic of the bias term, but I think it's better if I leave that for the next video so that I don't make this video way too long. So I will end here. Thank you kindly.